Hello everyone, again this is Elise and I'm going to go over gluconeogenesis and the chemistry of that. We're going to keep this video just a basic overview. We're going to only focus on one particular molecule getting converted. So in this case, we're going to look at lactate or lactic acid. In gluconeogenesis, you can have lactic acid, you can have triglycerols, you can have amino acids and different non-carbohydrate sources that get converted back into glucose. So that's what this process is going to go over. So let's go ahead and take a look at it and why this would occur. So again, gluconeogenesis is going to happen in the liver or kidneys. It's going to get triggered when we have low blood glucose levels and we need to raise those blood glucose levels back up so then that way we don't pass out, that all of our cells in our body are actually getting enough glucose. So first, usually what's going to happen is that we've gone through glycolysis already. So we've taken this glucose molecule and we've already converted it into pyruvate. Gluconeogenesis is pretty much the reverse of this glycolysis process. So we're going to use special enzymes that are found in the liver or in the kidneys that are going to reverse this process. So I wanted to go ahead and just show you the glycolysis just in pictures. I kind of drew it out again. The black arrows mean that these steps right here are non-reversible, so we'll definitely need to pay attention to these. And in gluconeogenesis, there's going to have to be some sort of loophole or other way for us to overcome these three steps. Because again, we can't directly just reverse this process because these steps aren't reversible. So how do we go from pyruvate back to glucose so we can send the glucose out back the cell and raise our blood glucose levels? All right, so we're going to focus on the next steps and how our liver and kidneys do this. Okay, so once we've made pyruvate after glycolysis, usually if there's oxygen available, that is going to get sent to the mitochondria where it'll go through the Krebs cycle. I apologize if that's a little small, but it'll go through the Krebs cycle. And the Krebs cycle is a bunch of steps, intermediate steps here of chemical reactions that lead to certain products, one being acetylcholine. But in this case, we're really not going to focus on that because once the pyruvate is in the cell here, what is going to happen is if we have low blood glucose levels is that the pyruvate carboxylase enzyme is going to get activated and it's going to actually overstep all these steps. It's going to skip all these steps and go directly from here, from pyruvate, to one of the last steps in the Krebs cycle. So it's actually going to create this chemical known as oxaloacetate. And I abbreviated that OAA. And so what happens is we're taking a 3-carbon molecule, and in essence, we are creating a 4-molecule carbon molecule from that. And how do we do that? How do we add this extra carbon? Is we're going to take carbon dioxide, this enzyme is pyruvate carboxylase, and it's going to add that carbon to the end of here to give us oxaloacetate. Okay, so this is what's happening in this step here. It's one of the first steps in gluconeogenesis is that we have to create oxaloacetate. So next, once we've actually created that, and again, this is happening in the mitochondria, glycolysis is in the cytoplasm. This step right here happens in the mitochondria, all right? So the next step, what we're gonna do is that oxaloacetate or OAA can actually undergo a reversible reaction between another chemical called malate. And the reason why that is because they are so chemically similar. The only difference between them is a hydrogen. So what will happen is we'll actually take the NADH molecule, and I don't think you can really see that, so I'll write it a little bit bigger here. NADH, and we're going to strip that hydrogen using this enzyme called malate dehydrogenase. And again, it can add or subtract the hydrogen. So again, that's why this process is reversible. And in this case, it's going to strip this hydrogen and add it to the malate right here. So we're going to add a hydrogen to this 4-carbon molecule and then Once this is stripped, that actually gets converted to NAD plus. So now we've gone from OAA to malate. And again, the only chemical big difference between the two is an extra hydrogen. So now we have malate here, and malate can actually now leave the mitochondria. In that form, it's able to leave the mitochondria and go back out into the cytoplasm. So that's what's going to happen in the first three steps. Okay, we're going to go from pyruvate and go through and make that into a malate. All right, so now I'm going to add this part 2, so bear with me. And I'm going to put it next to because we want to make sure that we can see the glycolysis steps, because part 2 is going to be very relevant to what's going on. Now, remember, gluconeogenesis is happening because the blood sugar levels of the body are low. Usually sometimes too, like say we're exercising a lot and we have a lot of lactic acid that's building up. That lactic acid can actually come into the cell here. Lactic acid. And it can get converted into pyruvate. So how do we take lactic acid and actually create glucose from that? Is that lactic acid is going to enter the cell when it's under stress and has low glucose levels, and the muscles are using fermentation because there's no oxygen, and it's going to get converted into pyruvate. So just wanted to throw that out there as the example of how we're using lactic acid in this example. Okay, and this is going to come from outside the cell because of the muscles. They're being extra stressed and they don't have a lot of oxygen, nor do they have a lot of glucose. Okay, so I'm sorry I didn't throw that in before. So now let's go ahead and go to step 4. So we made malate, right? Malate is outside of the mitochondria now. It's left. Ooh, make sure you can see that. Malate is outside of the mitochondria. It's left the mitochondria. And what's going to happen is that malate dehydrogenase, once it's actually outside of the mitochondria, is going to convert it right back into the OAA. So it's going to remove that hydrogen. So we're going to take NAD plus and convert it back into NADH. That removes this hydrogen, and now we are just left with this 4-carbon atom. And again, it has to do this because OAA can't leave the mitochondria where malate can, but then it wants to convert it back to OAA. And the reason why that is because OAA is easier to convert into our next step. So we are actually going to convert OAA back into PEP, which was this step here in glycolysis. And why are we doing that? Well, because we can't take OAA and actually convert it into pyruvate, because remember, this step right here is non-reversible. So if we actually go back and create more pyruvate, we're not going to be able to reverse this whole glycolysis steps. So we actually have to overcome this, and we have to directly kind of like skip over pyruvate and convert it back into PEP. So that's what OAA will eventually turn into outside in the cytoplasm here. And that's going to happen through this special enzyme known as phosphoenol pyruvate carboxykinase. So not only is it going to take off one of these carbon molecules, but it's actually going to add a phosphate back into it. So it's a pretty big process for this enzyme here. So again, in this step, we're taking OAA and we're going back into PEP, which is a molecule found from the glycolysis steps. Okay, remember, we're trying to reverse all of this. So now that we've actually made PEP, we can go all the way back up to this point because, again, all these arrows are red and it's reversible. So these are going to be reversed till we get to this step. All right, so once we're at this step, we are stopped at the fructose 1,6-bisphosphate, right? We're at this step where there's 6 carbon molecules and there's 2 phosphate groups on each side. So we can't convert this normally on our own in normal cellular mechanisms or states. Okay, so we actually have to recruit a special enzyme that will allow us to reverse this process. This enzyme won't be available during glycolysis during normal cellular conditions. This will only happen when we have that low glucose levels in the blood and it's triggered that this enzyme be made. So it's not always going to be present in the cell. It has to be triggered to be made, so then that way we can actually reverse this process because, again, we need glucose. We have low blood sugar levels, and that's not good. So this enzyme will actually convert it back into fructose 6-phosphate. And from there, fructose 6-phosphate, remember this step is reversible, so it will be converted back into glucose 6-phosphate. Okay, so that's what happens at this step. Okay, we're going from fructose 1,6-bisphosphate to fructose 6-phosphate. Then fructose 6-phosphate can go to glucose 6-phosphate. Now we're here. Again, we've ran into a roadblock because, again, this step isn't reversible. We can't go from glucose 6-phosphate directly to glucose. So we have to do one last step. The cells have evolved where there's a specialized enzyme inside of what's called the smooth endoplasmic reticulum, which is an enzyme. There's an enzyme inside of there, and the smooth endoplasmic reticulum is an organelle that does a lot of different things, including like detoxifying the cell, lipid synthesis, all sorts of different functions. And so the glucose 6-phosphate will travel into the smooth endoplasmic reticulum organelle. And there, the enzyme is going to cleave off this phosphate, and it's going to create glucose. And then glucose can now leave the smooth endoplasmic reticulum and enter the cell. Now, remember that I said in the glycolysis video that glucose, once it doesn't have that phosphate there, can enter or leave the cell whenever it wants. Okay, so what will happen in the next step is because there's no phosphate on this glucose and it's in its pure form, this glucose can now leave the GLUT receptors of that particular cell and go out into the blood. Okay, glucose can freely go in and out of the cell. It gets trapped in here when it gets added a phosphate. Okay, that's how the cell knows it needs to stay inside. But once that's off, it's free reign. And now we've actually reversed the whole entire process. And the result of that is our blood glucose levels are going to go back up. And that is one mechanism in which our body uses to make sure that we can maintain homeostasis of those glucose levels. So again, this can happen with lactic acid. This can happen with triglycerides, amino acids, different non-carbohydrate things that trigger this. But I use lactic acid and as this example that would trigger the cells with other hormones and other signals to make pyruvate and then go through this whole process. Okay, so hopefully that explains that in a simplified way, and I hope you enjoyed this.